Hello everyone, my name is Seth Williams, and this is my presentation over Kirchhoff's voltage law and Kirchhoff's current law. This presentation will be a quick review over both laws and how they can be used to solve simple circuits. First, I just want to talk about the creator of KCL and KVL. His name is Gustav Robert Kirchhoff. He was born in Prussia, and when he was in college, he presented the laws in 1845 while working with Franz Neumann, a very famous mathematician at the time in Europe. So for Kirchhoff's voltage law, he simply states, in any closed loop network, the total voltage in the circuit around the loop is equal to the sum of all the voltage drops within the same loop. Now here are two diagrams to further explain his definition. So we see that the voltage from A to B plus the voltage from B to C plus the voltage from C to D, D to A will all equal to 0. So this is called a nodal equation. However, when writing the nodal equation, you also have to put polarity into account. So here, we have the current flowing clockwise, as shown by this figure. And from negative to positive, because it's flowing clockwise, the current will flow from negative to the positive terminal through this voltage source. We give it a positive value in the nodal equation. So this is negative to positive, positive, positive to negative will have a negative value, positive to negative will have a negative value. And all of those added up together will give you 0. However, if you see here, you can rewrite this equation to look like this. So you can actually rewrite it to have these two values positive and these two values negative. So it doesn't matter which way you determine if a voltage is positive or negative. You just have to be consistent. So if you say E1 from negative to positive is a negative value, you put it in here negative E1, then for every time it's negative to positive, you have to do negative. So what I mean by that is this E1 would become negative, V1 would become negative, and then V2, the voltage across V2, would become positive, and E2 would be positive because it's going from positive to negative. Personally, I prefer if in the direction is negative to positive, I give it a negative value in the nodal equation. It's easier to remember, it's very straightforward, you don't really have to think about it. Negatives first, give it a negative value. So although this diagram shows positive for E1, I personally would give it a negative, and the same for V1, and then positive for V2 and E2, because it's positive first, negative second. Anyways, so that's just a quick explanation of Kirchhoff's voltage law. So now I wanted to do a quick example. So in this example, I have this diagram here with 4 branches. There is a 45 volt voltage source, a 5 kilo ohm resistor, a 10 kilo ohm resistor, and a 7.5 kilo ohm resistor. And they are all in series. So, using KVL, you can solve for the current through this loop, since current is the one value we do not know through this circuit loop. We know the voltage, at least, we know the voltage here, we know the resistance here, resistance here, resistance here, but we don't know the current through. The current will be the same because it's a series, so to find the current, we will use KVL. So to set up the equation, you do here, since we're doing it clockwise, let me just draw. The current is flowing this way. It's going to be a clockwise loop. We have negative first, positive second. So from negative to positive, I gave it a negative V45. This means voltage of the 45 volt voltage source. Now, for the next one, we have positive and negative for resistor 1. So voltage can be rewritten as V equal to IR. So the voltage through the resistor 1 will be equal to I times R1, which is why here I have IR1. Similarly, I have IR2, which is, again, positive to negative, and IR3, positive to negative. And those are all added up together to give you 0. Okay. And again, V45 is negative because in a clockwise current, it will flow from the negative to positive, and so in this case, I determined that from negative to positive will be a negative value in the nodal equation. So now that we know the value for the voltage source and the values for the resistors, we can just plug everything in and solve for I. So we'll have 5 times I, because the 5 kilo ohm in R1, plus 10I plus 7.5I is equal to 45, because V45 was equal to 45 volts, and since it was negative, when we moved it over to the other side of the equal sign, it became positive, and therefore I is equal to 45 over 22.5, which is roughly 2 milliamps. So this method can also be applied to solve for unknown voltage values or resistance values for each branch of a loop. So say you knew every resistor and you knew the current, but you wanted to find the resistance, you could find it using similar nodal equations and solve for whatever resistance you want to find. Or if you need to find the voltage source, as long as you know enough information to use your nodal equation, you can solve for almost anything in a simple loop circuit like this. Now on to Kirchhoff's current law. Similar to KVL, KCL states total current or charge entering a junction or node is exactly equal to the charge leaving the node, as it has no other place to go except to leave, as no charge is lost within the node. So here we have a diagram. We have 3 currents coming in and 2 currents leaving the node. So the currents going in are given a positive value and the currents going out have a negative value. But similar to KVL, that can be flipped. You can have currents in being negative and currents out being positive. Either way, as long as you're consistent, this nodal equation will always work. Personally, I flip it again. I do currents in negative, currents out positive, which is what you will see in my example. So, for the KCL example, we have a circuit with 2 independent current sources. Now that's important because it will be harder to solve a circuit with KCL if there is a voltage source, and I will explain why later. So there are 3 nodes. There's V1, V2, and V0, and I have them labeled V1, V2, V0. V0 is the reference node, and it has a voltage value equal to 0. It's also called the ground. So the first nodal equation for KCL is negative IR1 because it's going in to the node V1, negative I1 because this current source is going in, and positive IR2. Now, you can rewrite I, like in KVL, how you rewrote V, for I is equal to V over R. And V is the difference of voltages across a branch. So V is going to be negative V1 minus V0 over R1 minus I1 plus V1 minus V2 over R2, which is equal to, and all that together is equal to 0. IR1 and I1 are negative because they go into the node, and IR2 is positive because it is leaving node 1. The second node equation is negative IR2 because it's going in, positive I2, positive IR3. And again, rewriting it with Ohm's law, we have negative V1 minus V2, negative V1 minus V2 over R2 plus I2 going out plus V2 minus V0 over R3. And now both equations can be simplified. We have negative vi over 4 minus 2 plus vi minus v2 over 2 equals 0 for the first one. What we did there is just plugging in the resistance values that we are given. So R1 is 4, R2 is 2, and R3 is 1. So for negative 2 is the value in milliamps for I1, and this 2 is the resistance 2, which is 2 kiloohms. Simplifying that further, you can get negative V1 plus 2Vi minus 2V2 is equal to 8. And similar to the second equation, you can simplify it by plugging in the known resistances, simplifying it further. Now you have two systems of equations. You have V1 minus 2V2 is equal to 8, and minus V1 plus 3V2 is equal to negative 2. And then simply you can solve for both V2 and V1 very simply. In this case, V2 is equal to 6 volts, and V1 is equal to 20 volts. A little bit more about KCL, and to wrap this all up, like KVL, you can manipulate the nodal equations to solve for unknowns given in any circuit containing nodes with only current sources. Because as I said before, if you have any voltage sources, it's harder to determine. Let me go back. Because you can't use Ohm's law in that case. Because if you need to know the I value and you're given a voltage value, but there's no resistance in that voltage source, you can't do V over R because there's no R for you to do over. So it's a little bit more complicated. So I wasn't going to talk about that in this presentation, but just wanted to talk about that. And then second, if there are voltage sources in the circuit with multiple loops, it might be more useful to use KVL and or loop mesh analysis, which I will not be talking about, but I'm sure you know what I'm talking about, because in class we realized going through each loop you're able to use a voltage source and rewrite it as I times R, and it makes solving circuits with voltage sources that have multiple loops easier. And that will wrap everything up. This is my list of references where I got all my diagrams from and all my information, and thank you for watching.